Hello everyone, this is the second part of chapter 2 in chapter 10. In the first video we discussed about the three different laws: the Charles law, Boyle's law, Avogadro's law, and the ideal gas equation. So in this video we're going to see the applications of these three laws along with the ideal gas equation. So what I'm trying to do in this video is I'm going to do some of the sample exercises which we can able to use, which law are convenient for what kind of problems. So let me start with an example of a decomposition reaction. For instance, if you have calcium carbonate, which is a solid compound, when it is heated, it's changed into calcium oxide and carbon dioxide gas. This is a decomposition reaction, as you know from 101. And any reaction, as you know, has to be balanced. So as you can see from this equation is already balanced, so we don't need to balance the equation. So the question here is that if you have a sample of calcium carbonate, if it's decomposed and the carbon dioxide gas and it's collected in a flask, says the flask has a size of 250 milliliter of flask. When the decomposition is complete, the gas is collected and kept in the atmospheric pressure, more than the atmospheric pressure actually, kept under the pressure of, 1.3 atm. It is seen on a pressure of 1.3 atm, so you have carbon dioxide gas here. And the temperature of the flask inside would be around 31 Celsius. Now the question is, how many moles of carbon dioxide gas was generated? So we have some kind of stoichiometric equation here. We would like to know how many moles of carbon dioxide gas were generated. So how do we solve a problem like this? The first thing, in order to solve a problem like this, what we need to know is we need to find out what are the given factors. We have the volume. The volume is given 250 milliliter. The milliliter has to be changed into liter. So if you want to change the milliliter into liter, you divide 250 by 1000. If you divide 250 by 1000, that gives you about 0.250 liter, and you have a pressure of 1.3 atm, and also you have a temperature of 31 Celsius, but 31 Celsius has to be changed into Kelvin because that's one of the SI units. Especially when we are dealing with the ideal gas equation, we intend to change Celsius or Fahrenheit to Kelvin. So what you have to do is you add 273 to 31 to change into Kelvin. That, I guess, will give you about 304. There is some decimal number, but we can change 304 Kelvin. So once we do that, then the next things we're going to look is what kind of equation are we going to use here. Are we using the Boyle's equation, Charles equation, Avogadro's equation, or ideal gas equation? So remember that you have temperature was given, pressure was given, volume was given. The R value is given to you. So the R value is going to be 0.08206 L atmospheric mole per Kelvin. This is one of the R values that we're going to use here. Now it's not my choice. The choice of the units actually comes from, because we have atm here, we have mole here. Actually we're looking for the number of moles, and we have a Kelvin value. So in order, the best formula to solve this problem, to find out how many moles of carbon dioxide were generated, it's going to be the ideal gas equation, which is PV equals to nRT. the R value will be given to you, but you should remember this formula. So from here we can able to calculate N. N would be PV over RT, which is going to be, the pressure will be 1.3 atm times the volume is going to be 0.250 liter. Okay, so the R is going to be 0.08206 and the temperature is going to be 304. So first let's multiply 1.3 by 0.250. So that gives you if you multiply 1.3 by 0.250, I believe it gives you 0.325 over, if you multiply the denominator part 0.08206 by 304, which is the temperature in Kelvin, that gives you about 24.9. So the unwanted units will be cancelled out and you will have the mole value. So now we have to divide 0.325 by 24.9. So that would give you around, I'm going to write down here, I have some space here, 0.013 mole of carbon dioxide. Mole of carbon dioxide. So the question is, if you have a calcium carbonate, when calcium carbonate is decomposed, and if you like to know the number of moles of carbon dioxide that has been calculated, you can use the ideal gas equation. This much mole of carbon dioxide were generated. Sometimes you'll be interested to find out the amount in grams. So if you like to know the amount in grams, what you have to do is you multiply 0.013 mole of carbon dioxide by the molar mass of carbon dioxide, which is oxygen has 32 plus 12. 32 plus 12 gives you, I believe, 44. I believe 32 plus 12 is 44. So if you multiply 0.013 by 44 grams of 1 mole of carbon dioxide, that would probably give you about 0.572 grams of carbon dioxide. So this much carbon dioxide will be collected from the decomposition reaction of calcium carbonate. Now the ratio is going to be 1 to 1. So for 1 mole of calcium carbonate you get 1 mole of carbon dioxide. So the ratio is 1 to 1 here, so we don't need to do further operation. If this was 2 to 1, then we have to change the number of moles of carbon dioxide that would correspond with the number of moles of calcium carbonate. But in this case, we are so lucky that this ratio is a 1 to 1 ratio. So basically the gas laws we discussed in this chapter, mostly they are related with the ideal gas equation. So the ideal gas equation, we can able to play around with the ideal gas equation, which is PV equals to nRT, and related to one of the 3 laws, the Boyle's or the Charles or the Avogadro's law. For example, when we want to hold the N and the T are constant value, when you are assuming N and T, which is the number of moles and the temperature, are constant, also R is going to be constant. So that provides you that PV is a constant value. Now if PV is a constant value, which I say K, this is pretty much related with the Boyle's law. So if the number of moles and the temperature are constant, the value of pressure and volumes are the ones that are interchanging to each other. However, the product PV is always the same. So this implies that P1 V1 equals to P2 V2, which is a direct implication of Boyle's law. It's a direct implication of Boyle's law. So we can use the Boyle's law to determine how the volume of gas changes when the pressure changes, because Boyle's law pretty much is interested in the relationship between pressure and volume, and we know that volume is inversely proportional to pressure under Boyle's law rules. So if you have a cylinder with a movable piston holds about 50 liter. Okay, let's say if you have a volume, let's say I put the volume 1 with be 50.0 liter. It will be like nitrogen, a 50 liter of nitrogen, we have a pressure of the nitrogen would be at initial value would be about 18.5 atm, which is the atmospheric pressure, which is standard pressure, and I'm going to consider the temperature will be 21 Celsius. And the question would be, what volume will the gas occupy if the temperature is maintained at the same, which is 21 degrees centigrade, while we want to reduce the pressure at 2 atm. Okay, now remember here we're talking about nitrogen, so the number of moles is constant, it's never been changed. So we have a piston here. Initially we have a 50 liter of 50.0 liter of nitrogen under 18.5 atm. Okay, the temperature is constant, which is 21 Celsius. Now we wanted to reduce the pressure. Instead of 15.0 instead of 18.5 atm, we have the same container, but this time we will have, what did I say, 2 atm, and it's still the same substance, which is a diatomic molecule nitrogen, and the temperature is also the same, 21 degrees centigrade. So I'd like to know, if I reduce the pressure from 18.5 to 2 atm, what would be the volume? Do you think the volume will be high or the volume will be low? Obviously the volume is supposed to be much higher, because Boyle says that volume is inversely proportional to pressure. What it means that if you reduce the pressure, if the pressure is low, the volume is going to be high. But let's see that if this works for us or not. So this is a direct implication of Boyle's law, and the Boyle's law says that P1 V1 equals to P2 V2, which means that we have all the values here except the new volume, which is going to be V2. So V2 is going to be P1 V1 over P2. So according to Boyle's law, we can deduce that V2 equals to V1 times P1 over P2. So we know V1 is 50.0 liter, and first pressure, the initial pressure, was 18.5 atm, and we'll be very interested to know what should be the new volume if you reduce the pressure into 2. P2 is 2, so 2 atm. So let's do this. If you divide 18.5 by 2, we would get about 9.25. So if you multiply 50.0 by 9.25, that will give you approximately 9.25 by 50, which is the volume, the initial volume, would give you about 462.5 liter. So what is observation here? Under pressure 1, when the pressure 1 was 18.5 atm, the volume was 50.0 liter. When you reduce the pressure from 18.5 atm to 2 atm, to 0.0 atm, the volume becomes to 462.5 liter. So this is a direct consequence of Boyle's law. Boyle's law. What Boyle's law says that volume is inversely proportional to pressure. Volume is inversely proportional to pressure. You increase the pressure, you decrease the volume, or vice versa. Alright? So this is one of the problems. The second problem is, let's say that if you have a gas pressure in a can, you have a can here, assume that there is a can here. In a can, the pressure is 1.5 atm. Okay, and temperature will be 25 Celsius, which is room temperature. And if this can obeys the ideal gas equation, that's a good information, because you don't need to worry about which law are you going to apply. If they tell you that ideal gas equation, then it comes to you that PV equals to nRT is the only solution for this problem. So what will be the pressure when the can is heated to 450 degrees centigrade? If you change the temperature from 25 degrees centigrade to about 450 degrees centigrade, and we'll be very much interested about what would be the new pressure. So you have pressure 1, which is 1.5 atm. You have pressure 2, we don't know, which is X. We have temperature 1. I don't have a place here, but I can say temperature 1 is about 25 Celsius, but you have to change the Celsius into Kelvin by adding 273. So if you add 273 to 25, I believe, so that gives you 298 Kelvin. And what would be temperature 2? Temperature 2 is going to be what? 450 Celsius. 450 Celsius, we add 273 into 8, we would get 723 Kelvin. Okay, so we have a lot of stuff here. We have pressure, we have temperature, we have the volume. So in this case, we'll be interested to determine that what would be the new pressure. So it looks like a little bit complicated, but we can able to deduce this formula here, PV equals to nRT. From PV equals to nRT, we can rewrite this as P over T equals to nR over V. Now, why I do this? If you noticed, N is the number of moles, it's constant according to the problem. R is a constant volume. R is a constant at 0.08206. L atmospheric per mole, and Kelvin. Volume is constant too. So all these values are constant. So if these values are constant, the ratio of pressure and temperature is always be the same. I mean, pressure and temperature can be different, but the ratio, when you divide them, they will give you a constant value, which means P over T, the ratio of P over T, can able to help us to determine the value of the second pressure. So the idea here is that P over T equals nR over V. What does that mean? P1, this is the same as P1 T1 equals to P2 over T2. We have a third ratio, that's going to be P3 over T3. Generally, you can say Pn over Tn, where n can be any number, any whole number, excluding 0. So this would be the best ratio to determine the unknown value of pressure, which is the second pressure. So P2 is going to be, from this ratio, we can use something called a crisscross if you want to. So P2 would be P1 times T2 over T1. That might be the best way to solve such a problem. Remember, you have interchange of pressure and temperature, so you're comparing the pressure and temperature by changing the temperature of the first one was 25 Celsius, which is 298 Kelvin. You bring up that from 25 from 25 Celsius to 450 degrees Celsius. You see, a very drastic change of temperature. When you change the temperature, what would happen with the pressure? Is this going to be less or is this going to be more? So the first pressure was P1 was I believe 1.5 atm. So we have T2, which is 450 Celsius, but 450 Celsius by Kelvin value is going to be 723 Kelvin. Temperature 1 was 25 degrees Celsius, which means 298 Kelvin. So my guess is that if you increase the temperature, obviously the pressure should supposedly be increased because there is a lot of collisions. There's going to be a great or huge amount of molecules will be collided. The more the molecules are collided, the pressure is going to be higher. But let's see how this is real in a mathematical equation. So P2 equals to P1 or times T2. So P1 is 1.5 atm times T2, which is second temperature, which is going to be 723 Kelvin, divided by 298 Kelvin. So 1.5 times 723 gives me about 1084. I'll divide that by 298 Kelvin. So 1284 by 298. Okay, it gives me about, if you do the mathematics, it gives you approximately 3.64 atm. So you can see that increasing temperature is an implication that increasing the pressure, because when you increase temperature, the molecule of the gases will be collided often. The more collision you have is going to be more pressure. So this is true. Theoretically, if you increase the temperature, the molecule of gases will be faster moving. Whenever they move faster, they collided with the container, whatever containers that you have, or a beaker or a flask, and that eventually creates more pressure. So we are facing with the situation where if you have, what would happen if you have pressure, volume, and temperature all changes at one time for a fixed number of moles. Let's say that the number of moles will remain constant and remain constant. However, pressure will be changing, volume will be changing, temperature will be changing. So you will have a situation that PV over T equals to NR. These are the only value which is going to be constant, because the number of moles is constant. R is obviously, R is a number which is 0.08206 mole per Kelvin. So if you have the three situations are changing at the same time, the new formula that you're going to use will be P1 V1 over T1 equals to P2 V2 over T2. So let me give you an example. Say, for instance, if you have an inflated balloon, the balloon has a volume of, the initial volume was, I would say V1 will be 5.0 liter at sea level. Okay, when I say at sea level is that the pressure 1 is going to be 1.0 atm. Now, what would happen here, this inflated balloon will be allowed to ascend until the pressure will be dropped to 0.45 atm. So when it goes down, when it's ascended, remember that the pressure is going to be reduced. So this is going to be our P2 value. Now, at this time, obviously the temperature of the gas falls from room temperature or the temperature in a sea level. Let's say if it is 22 Celsius, which is going to be T1, and it goes down to a very cool temperature, minus 21 degrees Celsius, because remember you are going down to ascending to the bottom of the sea level. So that's going to be cold. So you'll be asked to calculate the volume, the new volume of the balloon at its final altitude. So in this case, you'll be asked to calculate V2, which we don't know. So in that case, this is the best formula that will help us our situation. Why I say it is the best? Because pressure is changing, volume is changing, temperature is changing. The only values that are not changing is the N value and the R value. So we have to deduce V2 from here. V2 is going to be V1 times P1 over P2 times T2 over T1. So V2 equals to V1 times P1 over P2 times T2 over T1. Now remember, you may not remember all these, but you can deduce that from the ideal gas equation PV equals to nRT. Your source is that here the N and the R are the two values that are constant here. They are constant according to the equation. Everything is changing. Pressure is changing, volume is changing, temperature is changing from the problem. So that means PV over T is going to be a constant value, which implies that P1 V1 over T1 equals to P2 V2 over T2. That's how you can able to solve a problem like this nature. So let's go back here. So we know V1, the volume 1, will be 5.0 liter. So V2 is going to be V1 is 5.0 liter times P1 is going to be 1.0 atm over P2, the second pressure. We ascended down below sea level. It changes into 0.45 atm, and T2, the second temperature. Remember that the T2, since we go down, it was initially it was 22 Celsius, but we move into minus 21. That gives you, when you change into Kelvin, it gives you 252 Kelvin, and the initial temperature T1 was 22, which is about 295 Kelvin. So now we're going to do a little bit mathematics here. You can do whichever way you like. Maybe you can start multiplying 5 by 1. So that gives you 5 over 0.45 times 252 Kelvin over 295. So the best way is you can multiply the numerator part first. You can do this first, and you can do this second, and you divide them. So 5 times 252. That gives you what? That pretty much gives you about, let's say, 1,000. If you use your calculator, it gives you 1,620. Remember, the volume is in liter, so I'm going to put liter here, divided by 0.95 by 295. 0.95 by 295, that gives you so 0.45 by 295, that gives you about 132 approximately, 132.7 is in liter. So if you divide 1,260 by 132.7, approximately would give you 9.49 liter. So when you compare the volume at sea level was 5.0 liter. When it goes down, the volume is going to be reduced. The volume is going to be increased. Why that? If you think about it, the pressure decreased. If the pressure decreased, the volume is increased. Does that tell you something? Obviously, that's going to be Boyle's law. It's a Boyle's law. Boyle's law is inversely proportional to the pressure, because the pressure was initially 1.0 atm, but it goes down to 0.45 atm. So that means it brings up the volume from 5 liter to 9.49 liter. So this has a direct implication of Boyle's rule or Boyle's law. So this is one of the practices that we do related with Boyle's law, Avogadro's law, Charles' law, and ideal gas equation. What's important here to highlight this, the important point that please read the problem, break down the problem, make your analysis, identify what are given, write all the given values, and write what are the constant terms. That way you can tell, or you can see which of the 3 laws you may apply. Okay, so any gas equation, any gas problems, the best thing is sort out what is given, what's given to you, and what's known to you, and what are the constant values, and what's the unknown. That way you can easily see whether you use Boyle's, Charles, Avogadro's, or the ideal gas equation. This is all for today. I hope you like the video. Please share the video, and if you have any comments, please write me down the comment in the comment section. And if you like, please share it to your friend, leave a like, and share to your friend or Facebook or your classmates. Thank you very much, and I'll see you on the other videos. Thank you. Have a blessed day.